we introduced the idea of max-min. We said this is how you solve with calculus, but we gave the caution that there were 3 problems when you find a stationary point, or actually rather a turning point, right? We said there can be 3 things that get in the way of the turning point actually being the max or the min that you were looking for. And that was actually the thing I was focusing on. So do you remember what the 3 things were? Yeah. Discontinuous was actually the first one, right? So if the derivative that you get and the function that it comes from has some breaks in it, okay? You might find a turning point, but so what? The maximum might be somewhere else completely different, okay? Then we said, actually, yeah, we said, yeah, endpoints was the very last one because it was at the end. Then we said there could be other turning points involved, okay? Now, we covered all of these 3, and we had like sort of a little conclusion that sat at the end of our maximum problem that was sort of covering all of these, okay? So, I just gave you the general idea, and we went through one question. So, let's have a look at some concrete examples, okay? That's what I'm going to try and cover, just 2 today, all right? So, if you haven't jotted this down already, let's have a look through it. 2 positive integers add up to 8, okay? And we're going to get this third number n by squaring those 2 numbers and then adding up the squares. Okay? What's the smallest possible value for n? Now, by the way, I would assume this question might be worth 3 or maybe 4 marks, okay, as a max-min question. So even though they just say, what is it, right? They don't just want you to say, there's the number, that's it.
Though,
And well, that's exactly right. But yeah, it is. We're looking for you to actually show, well, how did you get that, right? And how can you justify that that must be the smallest possible value, all right? So, like most problems, right, that this is problem solving, they don't give you an equation. You've actually got to come up with an equation, right? And apart from n, there's no other actual values, names, pronumerals, that kind of thing. We have to make them all up, okay? So, let's begin by saying, let the 2 numbers, and you give them some names, right? So, what should we call them?
J1 and J2.
J1 and J2, possibly the worst. Yeah, I'm going to go with X and Y. Okay, nice and, could have done J's anyway. Be X and Y. Now, before I move off, all right, I've introduced these pronumerals, right? But what I want to pay particular careful attention to is the restrictions on these 2 numbers that appear in the question, okay? Now, in this case, they're really obvious. They actually get told you, namely, they're both positive and they're integers, okay? So you could say that in a couple of ways. You could say that they're greater than 0, right? But since we also know they're integers, you might want to go back to some of your year 8 set theory kind of stuff, and remember that this is a way to say positive integers. That Z is for integers. It's not an I, because I is for imaginary numbers, for those fun people who will do complex numbers later. So Z for integers, and the plus just means positive. Okay. So we've got our condition in there. Now we want to get some relationships between these 2 numbers, okay? And the rest of the question tells us those. So I've got these 2 positive integers adding up to 8, right? So therefore, x plus y equals 8. So far, so good. Okay. Now the last little bit of of information in the question is that this third number, n, right, comes from squaring and then adding them up, right? So n is equal to, you take the squares, x squared, y squared, you add them up. All right. Now we want the smallest possible value for this guy, okay? So you can see, like, this is what makes it problem solving, right? It's kind of like, well, what do I do next? What's the step? Like, what direction do I even need to go in? Okay. So here's my first tip, right? When you've got the quantity that you want to maximize or minimize, okay? In our case, it's to minimize. So that quantity that is to be minimized, what you want to do is express it in terms of one and only one variable, okay? So that quantity must be expressed. Now, you could say in terms of, right? But to give a bit more sort of mathematical language, we should say must be expressed as a function of one variable. Okay? So at the moment, what you've got is n is a function of x and y. okay? So you know how you're used to seeing f of x, right? So you might see, these two variable functions are actually quite common. We know heaps of functions that have lots of variables in them. Like say, the volume of a cylinder, right? The volume of a cylinder is a function of its radius and its height, right? So two variables, right? We've got two variables here. I've got to get rid of one of them because when I differentiate, I'm only going to differentiate with respect to one of them at a time, okay? You actually can differentiate with respect to one even when there's two other variables in there, but that's something for you to do if you do university level maths. Now, how can I get it in terms of just one variable and not two? I've got these two equations here, so I've got to use one of them in order to get rid of one of my variables. So what do you guys suggest? Okay, so I'm going to take that first equation there, right, and use it to get this substitution, okay? So if I take that value there, right, 8 minus y, and I pop it into this x squared here, right, I'm going to get rid of that. That tells me that I've got 8 minus y all squared plus y squared. So this is good. Now n is just a function of the one variable y. Okay, so this is a good sign. Let's simplify this out a little bit. 8 minus y all squared should give me... Okay, yeah, right, I'll get to the y squared. I'm just doing the order I got there. Plus y squared plus y squared. Happy with that? Yeah? So 2y squared, 16y, 64. That's n.